NURS 2533, Process of Human Diseases 1. So this is Unit 3, Part 2. So this is the immunity part of this. So we're going to look at the immune system. We covered the immune system in great detail in AMP2, so you have to refer back to those notes. I posted some videos from AMP2 and various other sources that I've recorded in the past on the immune system. They're on Blackboard, so please refer to those. There are no worksheets. This was something that Avinash did. So, a quick review of the anatomy of this. The immune system really is very much involved with the lymphatic system. The two are very much interconnected, but fundamentally we have the primary lymphoid organs, which are the bone marrow and thymus, and the secondary lymph organs, which are the adenoids, tonsils, cervical nodes, the ducts, the axillary nodes, so all the lymph nodes, the spleen, Peyer's patches, and that kind of stuff. So the primary lymphoid organs is where the immune cells are generated or become immunocompetent. The B cells are generated and become immunocompetent in the bone marrow. The T lymphocytes are generated in the bone marrow and become immunocompetent in the thymus. This again is just review. The secondary is where those immune cells end up going and are seeded to. So this is the reticular lymphatic tissue that where these lymph cells, where these immune cells surveil and act. The lymph nodes, I'm not going to review, but they have more afferent than efferent, so that the lymph can be slowed there and give more time. The whole point is that the lymphatic system is really a useful place to do this, is because the lymphatics will draw up interstitial fluid and whatever is in the interstitial fluid and contain it and bring it to specific spots. So the lymph nodes are great spots for immunosurveillance. So immunity is really about protecting the body. Why do we need it? We need it to protect the body against invasions by anything that doesn't belong there. Microorganisms, pathogens, things like that. And really, I think one of the things that you have to kind of consider when you're considering the immunity and the immune response, and something that maybe we didn't cover so much in AMP2, is the idea that sometimes the immune system wins. Most of the time, the immune system wins. We have an invasion by non-self, and the immune system attacks that invasion and gets rid of that pathogen, that non-self. And hopefully there's not too much damage in the war that's being fought, and the organism recovers. Sometimes the immune system can't overcome, and the organism fails. So the immune system loses, the pathogen wins, and that's it. Death is the next thing. Sometimes there's a standoff as it were. The immune system can't eliminate the pathogen, but it can keep the pathogen under control. Uh, and and what ends up happening is you end up with these latent infections, um, things like herpes virus, uh, where the virus is never expelled from the body, but is rather latent. Uh, and then it manifests whenever the immune system is compromised in any way. So if there's any impairment, then to the immune system, then these latent infections can manifest again until they are brought back under control. Um, this is more common than you may think. There are a lot of little latent controlled uh, infections. Like uh, a lot of us have streptococcus uh, in our mouths, um, and it's just kept under control. There are latent all kinds of foreign uh, microbes. Sometimes these microbes are uh, are advantageous to have, and things like the intestinal flora and fauna. Uh, that's really an infection that we want the immune system to ignore because it's symbiotic. It it helps us. So so that's a concept that we really need to embrace. That that sometimes infections are just eliminated, we win. Sometimes infections win and we die. Sometimes the infection's latent, and sometimes it helps us. It could be any one of those reactions to the same microorganism. So, for instance, E. coli would be probably fit all four categories at various times and in various people. Um, so, an understanding of this also explains why some people are more susceptible to diseases than others, why having a strong immune system is considered an important aspect of health and healthy living, and a lot of what we consider preventative uh, measures that we take are all about that, making sure that the immune system wins or at least makes things latent. Now, in AMP2, we talked about there are two sections of the immune system. There's the innate immunity and adaptive immunity, or the non-specific and specific, if you were. The innate immunity really is about barriers, keeping the keeping stuff out. That's the first line of defense. The second line of defense are cells like uh, natural killer cells and phagocytes, dendritic cells, which are phagocytes. Um, so those are the two types of cells. Uh, Stuff like complement and interferon, which help uh, with the phagocytes primarily, and processes things like fever and inflammation. We, we talked, oh, the video previous to this was all about inflammation, but that's all considered part of the innate, non-specific. The adaptive immunity or the specific immunity really is got two uh, different venues, as it were. One is antibody mediated or humoral immunity, and the other is cell mediated immunity. In the humoral immunity, the the actions are caused by non-living extracellular secretions from lymphatic cells, from uh, from immune cells, and in the other the cell itself is involved in the action. Talk more about it in a couple of minutes. The specific immunity happens later than the non-specific immunity. The innate immunity happens first. It's minutes to hours. The adaptive immunity takes a couple of days. But when the adaptive immunity kicks in, the innate immunity doesn't go away. They all just overlap. So when we look at the features, the time of response is very rapid in the non-specific, and it's much slower in the specific. The uh, the innate immunity, non-specific, is really that. It's not very specific. It's limited to groups of microbes. So, um, like for instance, interferon works with all different types of viruses. They're not specific to a specific virus. Um, Neutrophils phagocytize bacteria. Doesn't matter what the bacteria is. So it's not. It's, so it works against classes of microbes. The adaptive is very specific. So each antigen has its own mechanism, and so there's a lot of diversity, and it can be very complex. Um, the the innate immunity only looks at general patterns, uh, but can recognize uh, self. So it identifies non-self, whereas the adaptive is very specific to specific things. Um, the innate immunity has no memory, so each exposure to the same thing will result in the same reaction. Um, Whereas adaptive immunity has memory and becomes better with subsequent exposure. It becomes more rapid, more efficient subsequently. Um, so the innate, the defenses are the barriers, cells, processes, and things. Whereas uh, the the adaptive immunity is mostly about cell killing. Phagocytes are the big important part in the uh, innate, and the lymphocytes, T and B lymphocytes, are the important ones in adaptive. We won't get too much into the molecules that are used, but complement, antimicrobial proteins, uh, different mediators uh, for inflammation are all involved in the innate, whereas the not so much in the adaptive. Antibodies are the big uh, extracellular non-living things. Now, to sum up the whole thing, all of these um, are really directed on at having the phagocytes eat and eliminate the bad guys. So when we talk about complement slows down a bacteria, punctures a hole in it, cellular lysis, uh, and it it makes the bacteria become phagocytized. T lymphocytes, killer T lymphocytes, release the contents of cells um, into the interstitium where the phagocytes can eat them. Natural killer cells do the same. And so really removal by phagocytes is the ultimate goal of almost all of these things. B lymphocytes make antibodies that tag the antigen uh, that allows the phagocyte to grab it and eat it. So phagocytosis is a huge and important part of understanding immunity in general. I've already mentioned humoral immunity versus cell-mediated immunity. Now, I have posted videos that go deep into this, so this is meant just um, as a reminder of materials that you've already learned in previous courses. If you need to review to understand it better, please go back and look at those other videos that are posted in this Blackboard section. But humoral immunity, it's only works on the microbes, on the pathogens that are found extracellularly, that are found in the interstitium. The lymphocyte that responds is the B lymphocyte, and then it turns into plasma cells, and plasma cells secrete antibodies, and then antibodies end up eliminating the the microbes by tagging them. They mark them for destruction. They neutralize, they agglutinate, they precipitate, they activate complement, uh, and make the microbe become phagocytized. Now, the cell-mediated immunity is really the cells that are involved in it are uh, are the T cells. Now, the thing that sets off um, the cell-mediated immunity are the microbes found in cells. And there's two different types of cells that they're found in. One is they're found in the cells that have phagocytized them, uh, either in the innate thing or because of humoral immunity. Either one, they activate the helper T cells. The helper T cells are used to coordinate the attacks of everything else. Um, they they co-stimulate the cytotoxic T cells. The the phagocytized microbes in the phagocyte make that phagocyte something called the antigen presenting cell, and so they present the antigen primarily to the helper T cells. Now, the cytotoxic T lymphocyte are the more action-oriented ones. They respond to microbes that are hiding out inside our body cells, and their MHC1s are presenting an antigen. The MHC2s on the antigen presenting cells and the phagocytized cells are the ones that activate the helper Ts. the the T lymphocyte end up killing the infected cells. So they therefore eliminate the reservoirs of infection. They don't eliminate the infection, they eliminate the reservoirs, the places where the infection is hiding or stored. And they release those microbes into the interstitium. And then those microbes in the interstitium get tagged by the antibodies that humoral immunity is making, and then they get eaten by the phagocytes. So it becomes all interconnected. Again, review this on some of the other videos that I've posted. The adaptive immunity has memory, and this is a very important thing. So an antigen is presented. The primary response is is fairly small and it takes a little bit of time. Uh, so the primary response is takes longer and is not as efficient. It's not as large and it's not as efficient, but it does create memory cells. And the memory cells are just clones of the first cell that was activated. The secondary response happens with the second exposure of the antigen, and it is much quicker and really amplified and creates a lot more memory cells for the tertiary response. But the point here is that with the primary response taking 10 days to maximize, then the person gets sick. The next time there's an exposure, the response is so rapid and so strong that the person doesn't get sick. In this thing, it shows the green is antigen Y, and the purple is antigen X, and it's just showing that the primary response is the primary to that antigen. Okay, we talked in AMP, and again, review, about the different things that antibodies do. Antibodies neutralize, agglutinate, precipitate, activate, complement, enhance phagocytosis. And we also said that at that time that there were 5 fundamental classes of antibodies, and they are Ig for immunoglobulin, Ig MADGE, M-A-D-G-E are the 5 types. It spells the word MADGE, M-A-D-G-E. Now, unfortunately, the MADGE mnemonic doesn't give us the order of them. It just helps you remember that there are 5 and what their letters are. So we're now going to look at the different antibodies. So IgG is the predominant immunoglobulin. In your blood right now, most of the, over 75% is IgG. It is the one that predominates on the secondary response. When the B lymphocytes and the memory cells are activated and they clone and turn into plasma cells, this is what's getting put out predominantly, IgGs. They have a half-life of about 3 weeks, someplace around 20 days. And they are very rapidly deployed, and they work primarily as a tag. They stick and they neutralize and they activate complement. They're a hugely important one. Now, the IgMs are the next most common. So it's about 10% of the immunoglobulins. We see these mostly in the first response to antigen. They are large. They have they're really pentamers. There's kind of 5 units all stuck together, and they're mostly used for precipitation and agglutination. They are large enough that they stay mostly in the blood. They don't diffuse easily because of that. Um, they last for a little over a week, someplace around a week when after exposure. So IgMs are very important. Um, they are they make up about 10% of what we see. Now, the other three types, they're in much smaller quantities. So IgA is very much like IgG in its structure, but it ends up being secreted out of the body. So these are the antibodies that are found in your saliva, in your tears, in breast milk, um, and they act to enhance the barriers of the uh, of the innate. Uh, so what they're really good at is neutralizing pathogens before they even enter your body. By having these things in your saliva or in your tears means that the the pathogens don't even get through into the body, and they're kind of dealt with. They're neutralized before they even can get in. Now they persist for uh, about a week as well. They but a lot of them just get washed away. Uh, so it's almost doesn't matter how long they persist because they are in secretions. Um, the IgDs are a special class, uh, and what they end up doing is they function as the receptors on the lymphocytes. Um, they're involved with activating the B lymphocyte to a specific antigen. So, uh, because they are an antibody to an antigen, they can also be a receptor to that same antigen and are used that way. Now, they last about 3 days. So that means that the B lymphocyte must be constantly producing these things as new receptors. And it's probably a great idea to just keep on refreshing your receptors just to keep everything from having mistakes or like just removing the old ones and putting new ones out every couple of days is a way of keeping everything fresh and working properly. Now, the last type of antibody is IgE. It's the least abundant, but potentially one of the more important ones for understanding how the body reacts to certain things. So, what IgEs do is when the B lymphocyte that makes them gets exposed and to the pathogen or to the non-self protein or whatever is going to the antigen, as it were, the they get produced and released. Now, in circulation, they don't last very long. They last only about 6 hours, and that's why they're the least abundant. But if they encounter a mast cell or a basophil, then what they do is they bind to that basophil or mast cell, and then they last for months, for a long time. And what happens is basophils and mast cells are both involved with the inflammatory response. And and so it means that that antigen will create inflammation. Um, and therefore it kind of it increases the specificity of the inflammatory response. It means that antigens will cause inflammation sooner. Now, the inflammation is no different than any other inflammation, but because it's tagged and identified, it will happen quicker and more readily. Now, this gives us this gives us some protection, but it also means that if it goes wrong, we can end up with allergic reactions. This type 1 hypersensitivity that we'll talk about in a few minutes can happen because of these IgEs. They are, so if there are antibodies made to, say, um, a bee sting or pollen or something, something that is normally innocuous, they will cause inflammation because of this IgE bound to a basophil. Now, basophils are also useful in parasitic infections, so we see this as being a bit of a problem, um, or a bit of a defense, really, against parasitic worms. So they're involved with that, activating the basophils against parasitic worms. So antibodies, they neutralize, they agglutinate, precipitate, activate, complement. Those are the things that they do. So they'll target and remove from circulation these infectious organisms or toxins, proteins that aren't supposed to be there, and they recruit some of the effectors, complement. They enhance phagocytosis. They enhance inflammation. So they make it all happen more efficiently. So that's what they're for. And so in that way, they are key to protecting us. Now, because of this, they are also now useful in healthcare as a way of diagnosing or monitoring what's going on. So by looking at antibody levels, we can figure out what kind of an infection somebody has, or what's the stage of infection that they're at, or whether they've had it before. We can look at some of these things and say, okay, like, has this person been exposed to that before? We can use antibodies in a passive way by by making a serum. By for instance, if you're bitten by a rattlesnake, you don't have the time to make the antibodies against the snake venom to protect yourself, because you'll probably die before the immune system can do that job. So what we do is we give a little bit of that venom to large animals, horses or cattle, and they make antibodies against that venom. And then we harvest those antibodies, and we refine them, and we make a serum that we inject in a person that's been bit by the snake. So that's a very useful thing for protecting the population. We do this with things like tetanus, and so that's what the tetanus shot's about. We used to do it a lot for hepatitis. They're called gamma globulin shots. Increasingly, we're getting very good at creating these things for therapeutic reasons. So a real success has been made in the treatment of leukemia, one specific type of leukemia, where there are now antibodies, monoclonal antibodies, that are tailored to go after the cells in that cancer that are specifically going wrong, and they get removed, they get neutralized by these antibodies, and in effect a cure to that cancer. this is research that is very promising, and hopefully before your careers are finished, there will be a lot more of that. So uh, this is a summary. I'm not going to spend any time on it, but IgG is the dominant one. There's most of it there. They last 21 days. They they are involved with fixing complement. They don't have anything to do with um, mast cells, but they cross the placenta. And this is an important thing because a baby is born into the environment that the mother has been exposed to. So the mother presumably is making antibodies against the pathogens in that environment. So it's nice that when the baby is born, they already have the antibodies against those pathogens to at least protect them until their own immune system is up and running. IgMs, there's less of it. They last about 10 days. They're involved in uh, activating complement. IgAs, about 6 days. They're next, and you'll notice that this at first is in grams per liter, and by the time we get down here, it's nanograms per liter, much smaller quantities. The IgEs you see are the only ones that bind to the mast cells, and none of the other ones other than the IgGs cross the placenta. I spent some time in AMP talking about active versus passive immunity. Active immunity is when um, you make antibodies against an antigen. Your body does it. You get exposed to the antigen, you have the challenge, you and you end up with immunity, with memory and specificity to that thing. Now, there's two ways of doing this. One is natural and the other is artificial. The natural way is to get sick. When I was a kid, I got the measles, the red measles. When that was my challenge. I I mounted an immune response to it and I've recovered from it. So I have memory and specificity and I won't get the measles again. Most of you guys have had the MMR vaccine, which you're exposed to the antigen from the measles rather than the pathogen from the measles. So it's a vaccination, but that's still a challenge. You mounted an immune response to it, so now you have specificity and memory to that thing. In passive immunity, the antibodies that are circulating come from someplace else. Um, so the antibodies are given to you. So they're either given to you across the placenta or mother's milk, which would be the natural way of doing it, or they're given to you by injection, which would be the artificial way. Either way, you are protected specifically against that antigen, but you are not creating memory. So you're not protected the next time after the antibody titers have gone down. So this is on the diagnostic tools. What do we look at when we're looking at the immune system? Well, blood tests and such. So one of the things we talked about in the last section was C-reactive proteins. So when we see high C-reactive, that means there's some sort of an inflammation, often an infection. High immunoglobulins mean that you have an infection. So high levels of IgM we see in viral infections. So we can look at them and indicate that there's something going on. Low levels mean that you have some sort of an immunodeficiency. And we look at that to see why people are chronically getting sick. We can look at the amount of complement. So low levels means that you have some sort of a disease and you're using up the complement. So if we look at how much free complement there is and it's down, that means you're using it. So you must have some sort of a disease. We look at the amount of IgE specifically uh, to tell whether there's allergies. Uh, and we can use those IgEs and test the ones that are harvested to find out what the inciting allergy is, whether it's dust mites or grass or peanuts. We can, by looking at the IgE levels and looking at the specificity of the IgE, we can learn a lot. We can look at the number of cells, and this is very common. So neutrophil cells, when they're elevated, that means there's a bacterial infection. If we have immune deficiencies secondary to other things, they'll be low. If we see high eosinophils, that must mean there's a parasitic infection or it can be an allergic reaction. Because one of the things that eosinophils do is they clean up um, the IgE antigen complexes. If we look at a common thing to look at is that the amount of or the number of helper T cells, the CD4 cells, low levels are looked at to diagnose HIV. We also will look at autoantibodies. So, and these tests tend to be laboratory confirmations of clinical diagnoses, in that we don't make the diagnosis from them, but they are evidence that support the diagnosis. So if somebody's clinically presenting with rheumatoid arthritis, and you do the blood test and you see a high rheumatoid factor, then chances are good that it's rheumatoid arthritis as opposed to a different type of arthritis. So we look at these autoantibodies. So the antibodies that are mistakenly going after your own self, and the different types are implicated in different autoimmune diseases. So, for instance, myasthenia gravis has antibodies that are made against the acetylcholine receptors at the synapse, at the neuromuscular synapse, and it causes muscle weakness because those receptors get removed. We look at double-stranded DNA autoantibodies is indicative of lupus, where the antibodies are attacking your own cells that have DNA, etc. We'll talk more about those later. Okay, to change direction here for a second, these are the hypersensitivity reactions. Now, a lot of people, so this is not review from AMP. Everything else up until this time has been. So the hypersensitivity reactions are really reactions where the immune system becomes sensitized. Sometimes they're good, oftentimes they're not. So type 1 is probably one of the more common ones, and this is atopic or anaphylactic. Now, the atopic is mild and the anaphylactic is severe, but basically they're both type 1 hypersensitivity reactions. So what happens in these is that the B cells recognize an antigen, whatever that antigen may be, and then they secrete IgE antibodies. And as we learned, IgE antibodies bind to basophils and mast cells. And so now these basophils and mast cells are sensitized to that particular antigen. The next time you see that antigen, what happens is that will cause the release of the vasoactive amines from those sensitized mast cells and basophils. So the vasoactive amines would be things like histamine, uh, and that leads to inflammation, a very rapid response to inflammation. Now, this is probably a good thing in a pathogenic antigen. But when it's an innocuous antigen, like for instance, proteins in peanuts, it can be uh, detrimental. So CM stands for clinical manifestations, and the clinical manifestations of this vary, and it varies depending on how much binds to what mast cells, what basophils, and etc. So the clinical manifestations could just be hives, urticaria, or rhinosinusitis, itchy eyes, runny nose, eczema, some bronchoconstriction, maybe trigger an asthma attack, that kind of thing. Or they could be full on anaphylaxis. And anaphylaxis is bronchoconstriction of the entire pulmonary tract. It also will lead to hypotension, a systemic vasodilation that drops blood pressure. And that drop in blood pressure will manifest as increased heart rate, so tachycardia. So um, this can be a very dangerous thing. So what causes it is a specific antigenic trigger. And once you're sensitized to that antigenic trigger will be the trigger. So peanut proteins, various drugs, shellfish, dust mites, bee stings, whatever, pollen, whatever that antigenic trigger is, will trigger this type 1 response. Now, the only way to really treat it is to avoid the trigger. Yeah. So this is what happens, is that the first exposure to the antigen causes the B cell to produce IgEs. The IgEs bind to the basophil. The granules in the basophil are here. The next exposure to the antigen causes an activation, and it's really about cross-linking. We won't get into that, of the receptors, the IgEs that are on that basophil. The basophil then releases its granules, which is called degranulation. So that, and in the granules are the histamine and the cytokines and the serotonin and the various other things that cause the inflammation. So then what you see is inflammation. The next type is type 2, often called cytotoxic. Now, cytotoxic reactions are the ones that you want. So the IgM and the IgGs are released and by exposure to the antigen, and the antigen is fixed as part of the surface of the membrane, cellular membrane, of the enemy cell. We'll call it the enemy cell, the cell that needs to be attacked. And then that leads to cellular destruction by usually by complement, by tagging that enemy cell for cytolysis by complement. It also leads to phagocytosis through opsonization, that the phagocytes will target the cells that have the IgMs and the IgGs stuck to it. NK cells will cause those cells to die through apoptosis, um, and this is quick, and for the most part, this is how we want the system to work. But sometimes it's working against us. Um, it happens, like I say, very quickly. So some of the examples, and it's a good idea to be able to come up with examples of each of these. Hint, hint for test purposes. ABO transfusions. When you're type A blood and you're given type B, you make anti-B antibodies and you will agglutinate the B blood that you're given. And so that's that transfusion reaction. And that's the IgMs binding to that B blood. Hemolytic disease of the newborn, with erythroblastosis fetalis, is really when you've got an Rh negative mother who has been exposed to Rh positive blood, makes anti-Rh antibodies, and then her immune system will attack the fetus at uh, at some point and cause this cytotoxic type reaction. Myasthenia gravis, uh, thyroiditis. In your outcomes, where you want to be looking at some thyroiditis, graft rejection, uh, hemolytic anemia, autoimmune hemolytic anemia is all found here. Type 3 is an interesting thing. It happens a lot. Um, it's it's about immune complexes. So when the antibodies bind to the antigen, they have now formed a new thing called the antigen antibody immune complex. And this is supposed to be cleaned up and phagocytized. Um, but sometimes these complexes are either produced really quickly and faster than they can be phagocytized, or the phagocytes, for some reason, ignore them. And these complexes get deposited in the tissues. But in getting deposited in the tissues, they trigger the inflammatory response, and they can trigger a chronic inflammation, uh, and really change the function of the tissue. Um, these are long acting, and and it doesn't happen really quickly. Um, so um, an example of this would be serum sickness. Now, it used to be thought that serum sickness was caused by serum. It turns out it's not. It's caused by drugs. Um, and the drug itself is not is a hapten. The drug is not enough on its own. So when it binds with proteins in the body, it acts as an antigen, and then the antigen reacts with the antibody, and then that causes inflammation. If it happens in the skin, you get hives, joints, you get joint pain, you get proteinuria. Lymphadenopathies are in swollen lymph nodes. So classically, this is what you get, and it kind of ends up everywhere. Now, the type 3 immune complex hypersensitivity is what you get in lupus, and this is an important thing. So a lot of the symptoms that the person is getting when they have lupus is caused by this type 3 hypersensitivity, um, rather than anything else. It is autoimmune because it's autoantibodies creating these immune complexes with inappropriate self. Another place that we see this is people that end up with kidney problems, glomerulonephritis, post-streptococcal. Um, and people can actually end up in kidney failure and end up on dialysis because of this type 3. And what happens is these antigen antibody complexes get deposited on in the glomerulus at that filtration membrane, and they screw up the filtration membrane and cause inflammation there, which then means that the glomerulus and the filtration doesn't happen properly. So when we look at it, the antigen antibody complex, and it doesn't matter what it is, deposits in the tissue that causes binding to white blood cells, which release enzymes, free radicals, and cause inflammation that destroys the tissue. Type 4 are the delayed hypersensitivities. So the delayed hypersensitivities are not involving antibodies. That's probably the critical thing. The other three all involve antibodies. Type 4 doesn't involve antibodies. I will repeat, it does not involve antibodies. Which of the following hypersensitivity reactions doesn't involve antibodies? Type 4. So what happens in type 4 is that the helper T cells, the CD4 lymphocytes, encounter the antigen through an antigen presenting cell. And they release various chemokines, interleukins, and things like that. So the chemical mediators that we've talked about previously. And that causes inflammation and activating macrophages. But it takes a while. It takes a couple of days before the T lymphocyte will encounter this presented antigen in that form and cause this inflammation. So we see this in things like contact dermatitis, where you get something on your skin and it's like 6 hours later you end up with inflammation of the skin. But the most interesting one is this one, PPD, which is really the tuberculosis test. You've all had it. You know that when they put a little pinprick under your skin and they insert they insert the antigen for tuberculosis under the skin. What ends up happening then is you have a delayed hypersensitivity and you get inflammation at the site of that little pinprick if you've come in contact with that antigen in the past. So so it's a way of screening people to see whether they've come into contact with tuberculosis. If you have that reaction, then further testing is done to see whether you have tuberculosis or whether you've just been exposed to it. So autoimmune disorders are when this immune system, when the things that we want to happen kind of loses its ability to distinguish a foreign tissue from self. Nobody knows why on some people this happens and why it happens in the ways that it does. What we do know is typically it's type 2, it's the cytotoxic. It is the IgMs and the IgGs targeting the cells and causing those cells to die. Sometimes, in the case of lupus, it's a uh, immune complex. So it's the antibody antigen complexes that cause the inflammation and hypersensitivities. But either way, the self tissues get attacked and are damaged inappropriately. But like I said, nobody knows why. And because nobody knows why, how do you treat it? You really need to know the why in order to have effective treatment. So really all we do for these people is immunosuppressive drugs. So we give them prednisone and other immunosuppressive drugs to try and and treat this. There are various other drugs, but prednisone is a very popular one because not only does it suppress the immune system, but it also suppresses inflammation, and a lot of the damage is done by inflammation. Now, the autoimmune disorders that you're responsible to understand are lupus, MS, multiple sclerosis, and thyroiditis, Hashimoto's and lymphocytic. Um, you can, I want you to read about these things yourself. I've posted some um, specific videos on each of these. They're posted from a different course that a pathology course that I've taught. So don't worry that it says massage therapy as on the slides. It doesn't matter. It's still lupus. It's still MS. So please look at that stuff. The immunodeficiencies are when the immune system can't do its job. There's not enough, there's some sort of a defect, and the immune system can't do what it's supposed to do. There can be real bad consequences to this. Infections can really take over. Now, the deficiencies could be in the nonspecific, innate, or it could be in the specific. It could be in the T lymphocytes. It could be in the B lymphocytes. So it could be humoral or cell mediated. There's probably every step there is some disease that is a deficiency because of a breakdown of that step. Now, there's two types. There are primary and there are secondary. Now, the primary immunodeficiencies is that there is something freaking wrong with the way the immune system has developed, that it's not caused by any other intrusion. So usually it's congenital. It's got something to do with inappropriate genetics, that the person is born unable to activate T lymphocytes or something. Like there's something wrong, or that fever becomes uncontrolled. Yeah, there's all kinds of things like that, but it's usually congenital, but it could also be idiopathic. They just don't know why it happens. So when we look at this table, some of these are like, so some humoral ones, X-linked hypogammaglobulinemia, which means it comes from your mother and you don't have enough gamma globs, which is the ability to make IgGs, selective deficiencies, this kind of thing. We look at all of these, and there's humoral, there is cellular, there's combined, there's some complement disorders where you're not making the right proteins or the proteins aren't made correctly, etc. The point here is that primary has got something to do with congenital or idiopathic causes. Secondary is way more common. Secondary is the cause of the immunodeficiency is linked to something else, and we know what it is. Um, the it's a compromise of the immune system. So this could be drugs, chemotherapy, immunosuppressive drugs. Um, People that are taking prednisone for its anti-inflammatory effects will become immunodeficient because that's the side effect of the drug. Um, Various infections will do this. Measles is a bad one for it. AIDS is a secondary acquired immunodeficiency. That's what AIDS means. In your textbook, there's a mistake. I don't know why the mistake is there in this edition, um, but it lists AIDS as a primary immunodeficiency. AIDS is by no means primary, it's secondary. The cause of it is infection by the HIV, the virus. The So the immunodeficiency is secondary to the infection of human immunovirus. So that is immunodeficiencies. So in this lecture, we looked at and did a review of the immune system, innate versus adaptive, humoral cell in the adaptive immunity, primary and secondary responsives, active versus passive. What do antibodies do? The four types of um, hypersensitivity, compare and contrast. Very good thing to know for test purposes. Be able to compare and contrast the different types of hypersensitivities. We looked briefly at autoimmune diseases and primary versus secondary immunodeficiencies. Um, I have post I'll post videos on uh, AIDS, on lupus, um, and yeah, but they will be on separate videos. So the next part is part 3, infections.